Hello, today we're going to review Unit 7 for the AP Chemistry exam using some free response and multiple choice questions. Okay, so we have a reaction of solid carbon and carbon dioxide gas forming carbon monoxide. The total pressure in the container was monitored, and when equilibrium was reached, there was still some solid carbon remaining. So remember that solids do not affect your equilibrium position as long as you have some. Because it's a reactant, it has to be there, but the specific amount doesn't affect it. Now for part A, it wants us to write the expression for the equilibrium constant Kp. So for pressure expressions, it's always Kp equals, and we would do the pressure of the carbon monoxide squared, because there's a coefficient of 2, over the pressure of the carbon dioxide. You don't include the solid carbon. If it were a Kc or a Ka or Kw or any other K, basically, it's going to be in molarity and it will have brackets. But when you're doing pressure, you want to make sure that you use parentheses, and it's the partial pressure of carbon monoxide and partial pressure of carbon dioxide. It's always products over reactants. That one was 1 point. Okay, for part B, we want to calculate the number of moles of CO2 initially placed in the container. Initially is times 0, and we have 5 atm. So we have moles, and in the question they gave us the liters and the temperature. So we can use BivNert. Pressure initially is atm is 5 atm. Volume was 2 liter container. N is what we're looking for. Our gas constant 0.0821 for atm, and our temperature in Kelvin was 1160, really high temperature. So if you solve for N, you get that there were 0.105 moles of CO2 originally placed in a container to 3 significant digits. Now for part B was 2 points total. For your calculations there. Part C was worth 3 points altogether. So let's take a look at part C. For the reaction mixture at equilibrium, the partial pressure of CO2 is 1.63, and calculate the partial pressure of carbon monoxide and the value of the equilibrium constant Kp. Okay, so for this one, we need to use an ice chart, because we know that the initial pressure of the CO2 is 5, and we don't have any carbon monoxide to begin with. The solid doesn't affect our equilibrium position. And then at equilibrium, the pressure of the CO2 is 1.63. So because we have an initial and an equilibrium value, that's how I knew to use an ice chart. We don't know the pressure of the carbon monoxide, that's what we're looking for. But we do know that because the reactants are decreasing, the products must increase. And you use the stoichiometry, the mole ratio there, the carbon dioxide goes down by x and the carbon monoxide must go up by 2x. So if I solve this, 5 minus x equals 1.63, I know that x is equal to 3.37. And so if I do that 2 times, I know that my pressure for the carbon monoxide is 6.74. So the partial pressure of CO at that equilibrium is 6.74. Okay, and then the value of the equilibrium constant Kp. So expression from part A is the pressure of the CO squared over the pressure of the CO2. So the carbon monoxide is 6.74 squared, and then 1.63 for the carbon dioxide. So squared divided by 1.63, we get the value of Kp is 27.7. And that was 3 points total. So the point distribution was actually for part CI. Was just 1 point for getting that 6.74 atm, and for part II, that was 2 points. 1 for plugging in the numbers correctly according to the Kp expression you wrote in part A, and then 1 point for the final answer. Now, for part D, if a suitable solid catalyst were placed in the vessel, would the final total pressure of the gases at equilibrium be greater than, less than, or equal to the final total pressure of gases at equilibrium without the catalyst to justify? So it will be the same. Catalysts affect the rate of a reaction, but for a reversible reaction, it affects the rate of both the forward and the reverse reaction. So it will reach equilibrium faster, but that equilibrium position will be equal whether or not you decide to use the catalyst. And that was just one point. For part E, in another experiment involving the same reaction, we have a rigid 2-liter container with 10 grams of carbon plus carbon monoxide and carbon dioxide each at a pressure of 2. Predict whether the CO2 will increase, decrease, or remain the same. So a couple clues in this question. We have an initial of both things. So that's, and it's asking us to predict what happens. So that's my clue to use Q. And Q, the expression is the same as K. But we need to plug in whatever, it's not at equilibrium. So whatever the values are, which is 2 atm for both of them. 2 squared over 2 is 2. That Q is smaller than the 27.7 that we found for K. Because it's at the same temperature, we know that K is the same. So Q is too small, right? It's much too small. It needs to become larger and larger in order to reach equilibrium. That means I need to make more and more products to make the Q value get large enough. So if we're making more products, right, and here's our carbon plus carbon dioxide yields 2 carbon monoxide. If I need to make more products, my pressure of the CO2 will decrease as the system approaches equilibrium because we're going to make more products and use up the CO2 reactants. E was 2 points, one for saying that the CO2 will decrease, and the second point was for correctly calculating Q and comparing it to the K that you found earlier. Okay, so now here's a different pre-response question. Several reactions are carried out using silver bromide, a cream-colored silver salt, and they give you the KSP value. Okay, so the other type of solubility in Unit 7 is KSP. Write the KSP expression for AGBR. Now, whenever you're doing solubility, it's always going to be the solid salt breaking down into the aqueous ions. So when you're writing the KSP expression, it will always be only products because the solid is not included. And so there we are. It's in molarity, so we use brackets. Now it says to calculate the value for part B of silver ions in 50 milliliters of a saturated solution of AGBR at 298 Kelvin. The 50 milliliters here doesn't matter. We just want to find it at that same temperature. So they give us the value of KSP, and we can just plug that into our equation. And since it's just silver bromide being dissolved in water, I know that when silver bromide dissolves, it's going to dissolve in a 1-to-1 ratio, 1 silver to 1 bromine. So these two amounts will be the same. So effectively, I can just do the KSP, which is 5 times 10 to the negative 13 is equal to x times x, or x squared. And when you solve for x, you get 7.07 times 10 to the negative 7th with 3 significant digits, and that is your molarity. If it asks you to find moles, then that 50 milliliters would be important, but it just wants the molarity, so you're done. No one was just 1 point. Now for part C, a 50 milliliter sample of distilled water is added to the solution as part B. Okay, so now that 50 milliliters is important. All right. Which is in a beaker with some solid silver bromide at the bottom. That tells us that it's a saturated solution. The solution is stirred and equilibrium is reestablished. Some solid silver bromide remains in the beaker. Okay, so we're still a saturated solution. The value is the value of the silver ion concentration greater than, less than, or equal to the value calculated in part B, and justify your answer. It's the same. the same temperature, so our KSP is the same. So when we solve for X, we get the same value. So that's for molarity. If it was asking you for moles, there would be more moles dissolved. But since you have more moles and you have more liters, the molarity winds up staying the same. And that one was just 1 point, all or nothing. It's equal to because even though you're adding more water, more of the solid silver bromide is dissolved to keep that molarity the same. Okay, part D here, calculate the minimum volume of distilled water necessary to completely dissolve a 5-gram sample of silver bromide at 298. And they give you the molar mass, which is nice of them. So anytime you see grams, and especially if they give you molar mass, you should convert it to moles. So I have 0.0266 moles of silver bromide. And basically we're looking to find the liters, some number of liters, so that becomes equal to the 7.07 times 10 to the negative 7th molarity that we found earlier. Because the temperature is the same, KSP is the same, so the molarity in a saturated solution will be the same. So you just need to solve for X here, and you get a ridiculously large number of liters, which is kind of fun. But it's 37,600 liters to 3 significant digits, which is just a huge number of liters. But that's kind of to illustrate just how insoluble silver bromide is. It's very, very insoluble, so you need lots and lots of water to dissolve even just 5 grams of it. Okay, now for part E, a student mixes 10 milliliters of a different silver nitrate solution with 2 milliliters of a sodium bromide solution. Stirs. What will the student observe, and justify your answer with calculations? So they're trying to get you to notice that when you react silver nitrate with sodium bromide, it's a double replacement reaction essentially, and you'll form silver bromide and sodium nitrate. But the sodium nitrate is completely soluble, and so is the sodium bromide and silver nitrate. So the sodium winds up being a spectator ion, and the nitrate winds up being a spectator ion. So effectively, we just have our silver ions and our bromide ions reacting to form solid silver bromide. So when it says, what will the student observe, we're trying to get at, okay, will a precipitate form? All right. So what we can do is find the new molarity when you add these two solutions together. So I'm going to do for the silver ions, M1V1 equals M2V2. My original molarity is 1.5 times 10 to the negative 4, and I have 10 milliliters of it. What is the new molarity when I'm now at a total of 12 milliliters? And then the same idea with the bromide. M1V1 equals M2V2. My original molarity is 5 times 10 to the negative 4, and I have 2 milliliters of that. What is my new molarity when I'm at 12 milliliters? And for the silver, I get 1.25 times 10 to the negative 4th, and for the bromine, I get 8.33 times 10 to the negative 5. So now I can plug those two values into a Q expression. The silver times the bromide, and we get a value for Q that's equal to 1.04 times 10 to the negative 8. Oh, we need to compare that to K, which is 5 times 10 to the negative 13th. All right, so Q is much larger than K. Now, if we were to look at our solubility expression, which is our silver bromide solid dissolving into silver ions and bromide ions, if Q is too big, I need to make it smaller to reach K. And to make something smaller, to make the Q smaller, we need more reactants. We need fewer products. So to make that happen, I would go in the reverse direction, and I would make more solid silver bromide. So you would observe a precipitate would form. And yes, you need all of that to figure it out. So this was a 3-point question to get there. Most likely it would be a point for getting the molarities correct, the new molarities, a point for getting the correct value of Q, and then a point for correctly comparing Q and saying that a precipitate would form. Okay, so here's the last part of this long free response. We have the color of another salt of silver, silver iodide, it's yellow. Student adds sodium iodide to a test tube containing a small amount of solid cream-colored silver bromide. After stirring, the student observes that the solid in the test tube changes color from cream to yellow. Write the chemical equation for the reaction that occurred in the test tube. So for I here, we're adding sodium iodide to the silver bromide. And we're forming silver iodide and then sodium bromide. And you're supposed to recognize that the sodium compounds are completely soluble. So to find a net ionic equation here, we would get the iodine ions plus the solid silver bromide forming solid silver iodide, the yellow colored, plus the bromide ions. The sodium is a spectator ion. That was just 1 point. For part II, which salt has the greater value of KSP? The greater value of KSP would mean that it dissolves more, has more ions. So silver bromide must have the larger value of KSP because it winds up with more ions. And silver iodide is the one that is formed as a solid because it turns yellow. So it must be less soluble, so it has a lower value of KSP. Okay, now let's look at some multiple choice questions with her Unit 7. The molar solubility in water of silver chromate, and they give you the KSP value. I always recommend writing out the dissolution equation. So you wind up with 2 silver ions and one of these chromate ions. And then your KSP expression winds up being the silver ions squared times the chromate, like this. So to find the molar solubility, it's essentially for one compound. And if we're looking for one of those whole compounds, it's going to be, when we plug this in, this dissolves in a ratio where you get 2 silver ions for every 1 chromate ion. And X will be that molar solubility, because that's the solubility for one of the whole compound. So if I were to rearrange this, we have 8 times 10 to the negative 12. And let's simplify this down. This is 4x cubed. So you would go ahead and divide this by 4 and then take the cube root. So you would get this answer here, E, because 8 divided by 4 is 2. So 2 times 10 to the negative 12, and then the cube root. Okay, we have a reaction, and it's at equilibrium, and they give us the molar concentrations. What is the value of the equilibrium constant? So that's pretty straightforward. We just need to write the correct equilibrium expression. So Z is cubed, X is squared, Y. Always products over reactants. So now we can just plug in our values for cubed over 2 squared times 0.5. Solve for K. And when you solve that, you get K as 32. Okay, beaker X has 50 milliliters of distilled water. Beaker Y has 100 milliliters of 1 molar sodium chloride. Solid silver chloride is added to both of them. Thoroughly stirring, some solid silver chloride remains at the bottom of each. Which of the following is true? So the concentration of the silver ions is what we're looking at. All right. So solid silver chloride dissolves to form silver ions and chloride ions. Now in pure water, it does this in a way that this is 1-to-1 ratio. Even if it has a really small KSP, you're still going to have some silver ions in the water. So it's definitely not A. But in beaker Y, we've got some sodium chloride. So we have some extra chloride ions, which is going to shift the equilibrium position. And I should really use 2 arrows, but when I have those chloride ions, it's going to create more solid product, which will decrease the amount of silver ions. And that's called the common ion effect. So beaker Y has a smaller amount of ions of silver than beaker X. So the correct answer is C.